So I'm Sean Parent. My talk here is all the safeties. This is my Adobe title slide. I'm a senior principal scientist at Adobe. I run the software technology lab. Some of you might know some of the people who work in the software technology lab. Dave Sankel is one of them who's here. Dave Abrahams is another person, and Nick DeMarco, who's been getting involved with the standards committee, is the third member of our team. So our team is chartered with trying to improve software engineering practice, which we define as being distinct from process, meaning that we're concerned with how engineers write code, what are the actual lines of code that they type when they sit down at the keyboard, as opposed to whether or not they're following an agile process or a waterfall process or things along those lines. And specifically, we're trying to take a very long-term view at this, right? We're looking 10 years out. What direction does this go in? And at the same time, we're trying to create a usable stream of artifacts. So which means as we're working on papers, we're doing research, we're working on tooling, and out of all of that research, what we want is things that practically have an impact on the company so that we can pay for our group and justify it going forward. So that's what we do. So why am I here talking about safety? Well, the topic of safety has been looming large in the industry of late. It didn't start here, but this came out just last November. What you're looking at here is an NSA report titled Software Memory Safety. And they issued this report, and it specifically calls out C and C++ as memory unsafe languages. Right, some quotes from this: 70% of their vulnerabilities, they were talking about specific systems, were due to memory safety issues. And the NSA recommends using a memory safe language when possible. So fairly strong wording. Well, that got followed up by this report. This was January 2022. So not too far back. This is Consumer Reports. Actually, January 2023. I have the year wrong in my notes. So this is January 2023. This is Consumer Reports, right? Which you think about as, what kind of car do you want to buy? Consumer Reports issued a report on the future of memory safety, challenges and recommendations. And that has this quote. I'm not going to read the whole thing, but I'm going to call out that they're extending the issue of memory safety into stability issues of consumer products. Okay? So now we're not just talking about security. Now we're talking about product defects and product reliability. So that gets followed up by this report. This was just March, this last year, March 2023, the National Cybersecurity Strategy. Okay, this is what it has to say about cybersecurity. And this report also mentions memory safety. Basically, the hyperbole here is that all of Western civilization is in the state of an existential crisis, and it's because of C++. Good job. Now, the scary part of this report is they go through, there's 5 pillars in this report of strategic recommendations. The scary part is pillar 3. Why is pillar 3 the scary part? Because this has the most far-reaching effects on the industry. Hold the stewards of our data accountable. Okay? This is strategic objective 3.1 as part of pillar 3. What does that mean? It means if you're working on a product and the product deals with user information, now you are liable. It doesn't matter what it says in your license agreement. Okay? It doesn't matter that you require your users back up their data, that you require your users have secure passwords. There's an explicit shift here. Okay? that doesn't matter. You're now liable. And they call that out specifically. We're going to shift liability for insecure software products and services. And they're going to leverage the federal procurement to improve accountability. Okay, what does that mean? You can't sell your product into government agencies if you don't meet some minimum bar on security. Okay. How far-reaching is this on the industry? And why are they going this direction, right? Why is there this sudden expansion of scope from saying we're trying to secure, NSA is trying to secure the critical infrastructure, right? They're trying to secure the grid, they're trying to secure nuclear power plants, they're trying to secure the aerospace industry, and now we're talking about every product that's sold in the marketplace. The reason for that expansion is because the NSA went out and they talked to all of the people who work on critical infrastructure. And they said, what do you use to build your critical infrastructure? And the answer is open source software and commercial software, right? They write software. Some of us here probably work on critical software, but for the rest of you, the people working on critical software infrastructure probably write software pretty much the same way you do, okay? So if we want to secure the critical infrastructure, we need to secure everything. So that's the strategy. And it's not just the US. This is the Cyber Resilience Act from the EU, which includes the recommendation. This is the actual legal wording on it, but basically what this says is any manufacturer of a product with digital elements. So whether you're selling an Internet of Things device, or whether or not you are selling just a piece of software, that's a digital element, you're going to be responsible for complying with essential security requirements. Okay. Now, if you actually go and start to look at the legislation, both here and both in what's going on with the White House, what they're doing is they're saying, oh, if you are writing your systems in a negligent manner, then your liability goes up. 60 to 70% of the security vulnerabilities are due to memory unsafety and memory unsafe languages. So if you're using C or C++, maybe that's negligence. Okay? So what is memory safety? Right? If it's so important, what is it? Of the 4 reports I just showed, only the NSA report has any definition of what memory safety is. They all mention it. This is what it says. It's a very broad category of issues related to how a program manages memory. Great. Great. So, didn't mean to click past. So at least it goes on giving a few examples, right? They talk about buffer overflows, leaking memory, use after free, double free, use of uninitialized variables, and data races. Okay, so data races there is a little odd because typically when I think data race, I think thread safety issues and not memory safety issues. So the bucket they're putting this stuff in is very large. Okay, and not very precise. So obviously, memory safety must be a term of trade, right? It's something that's well defined in the computer science literature. So I could just go look it up. So I go look up, what is memory safety, right? I get a couple answers that are pretty good. It's kind of what we feel, right? It's about security vulnerabilities, dealing with memory access, such as buffer overflows, such as, right? Very precise terms here. A paper here that gives their definition of memory safety. It's very concise, but it has nothing to do with things like stack overflows. Okay. Then you have these very weak things. It's about dangling pointers. It's about touching memory in the operating system. Maybe it has something to do with race conditions. Maybe it has something to do with unwanted aliasing as opposed to wanted aliasing. I don't know. So this isn't very helpful. Right? So maybe we can back up. If we can't define memory safety, what is safety? Well, I went through scouring a bunch of literature looking for definitions. None of them were better than what the Oxford Dictionary will tell you. Just that safety is the condition of being protected from or unlikely to cause danger, risk, or injury. Okay. That's a little tough to connect to memory safety, at least indirectly, right? So, but an interesting thing, as I'm going through and I'm scouring the literature and I'm reading these papers, there's a bunch of papers about proving memory safety, or at least proving particular forms of memory safety in particular systems. And all of those start to have a common thread within them. And the common thread is they talk about safety properties. So what are safety properties? Well, safety properties go back to a paper in 1977 from Leslie Lambert. They're a foundational part of something called temporal logic. And this is from Leslie Lambert's paper. He's a Turing Award winner, if you don't know who Leslie Lambert is. So, and the paper is proving the correctness of multi-process programs. But if you go read this paper, it's a very good paper. If you go read this paper, it's equally as applicable to single-process programs, right? Multi-process programs are just a generalization of single-process programs. And he says, to prove the correctness of a program, one must prove two essential different types of properties about it, which we call safety and liveness properties. And very loosely, a safety property is one which states that something will not happen. Okay? And a liveness property is one that states that something must happen eventually. And he goes on to define these formally in temporal logic, and then to prove that you have to prove both of them to prove total correctness, and to prove particular properties about each of these things, right? And one essential asset, or one essential property of a safety property is that safety properties compose, right? And what I mean by that is if you can say that there is no way in your system to do a bad thing, or there's no operation in your system that will do a bad thing, then it doesn't matter how you combine all of those operations, there's no way for your system as a whole to do the bad thing. Okay? That's an essential property of a safety property. So the way that's stated in the literature is if every common execution prefix satisfies P, then the program satisfies P. The reason why it's a common prefix is because we're talking about execution instructions, and so we need to kind of wrap that up into an abstraction layer and say that as a whole is an operation. Okay. So as an example of a safety property, we want to say that our self-driving car, cannot drive off the road. Right? So a safe operation does not allow the car to drive off the road. If all the operations are safe, the car can't drive off the road. Right? It's pretty self-explanatory. That's assuming the preconditions are not violated. All of this is in the context of writing correct code and proving software correct. Right? So the assumption here is so long as our software is correct, and nothing allows the car to drive off the road, then as part of proving the total correctness of our system, we know that our car cannot drive off the road. An example of a liveness property is that the car will eventually reach its destination. Okay? It will get there. This may be achieved by a series of stepwise refinements. Liveness properties are very much an extension of loop invariants. Okay? If you think about a loop invariant, this holds until my loop terminates, and then the property as a whole holds. So safety in terms of safety properties. Now we can give a pretty precise definition of what safety means. The safety of a program is a set of properties that cannot happen given valid input. Okay? And we can extend that to what it means to have a safe programming language, which is where we're trying to get to, right? We're talking about memory safety in the context of programming languages, going back to the NSA report. So the safety of a programming language is a set of safety properties guaranteed by the language for any expressible program. Anything you can write in the language will satisfy this set of safety properties. Okay? So every program that can be written in the language, or a safe subset of the language, satisfies the safety properties of the language. So, how do you achieve safety in a language? There are 3 basic approaches, and every language will take some mix of them. Okay, every language that's going for safety. One is by limiting the expressibility of the language. Okay, the language doesn't let you express the bad thing that could happen, or doesn't it let you express something that would cause the bad thing to happen. So, for example, if you're programming in Haskell, you have no mutation. Without no mutation, you have no race conditions. Therefore, by limiting the expressibility within the Haskell language, you guarantee the safety of no race conditions. No race conditions is a safety property. The next is runtime validations. The program prevents unsafe, that's very poorly worded there, apologies. The program prevents some unsafe thing from happening by resulting in an error or termination. Right? So for example, the Swift language, if you have integer overflow, by default will trap. Okay? So to prevent that case. The third way that you can get safety is through defined results, which is where the program defines the behavior of what otherwise would be a potentially violating property. Okay? So our car's about to drive off the road, it's always going to turn back on the road. In the case of JavaScript, if you access an array out of bounds, what happens? You get an undefined result, where undefined is a value within the system. It's not an error. Okay? So you see this with floating point arithmetics. You do a divide by 0 with floating point, you get a nan. That's a defined result, okay, for an otherwise unsafe operation. So what is a memory safe language? Well, a language has no operations that access memory which is not allocated, has not been initialized, and has been released. Okay? So this is fairly common if you read through the literature. These definitions in some form appear almost everywhere. Okay. But there's a problem with this definition, right? This is nice. It can be implemented frequently very efficiently. I can use the MMU to protect my memory, to make sure that I'm only accessing memory very safely. Very nice software properties here. But if we go back to our car analogy and trying to keep our car on the road, what's going wrong here? Okay. Well, we're going to keep our car on the road, but we're not going to prevent our car from crossing into head-on traffic. Okay? We're not going to prevent the car from doing what the car isn't supposed to do. We're just putting guardrails around the universe within which it can operate. Well, what's the problem we're trying to solve with memory safety? Right? We haven't even stated that yet. We've been trying to define what memory safety is. Memory safety comes out of the security community. What problem is the security community actually trying to solve? Well, a secure system is a system where the resources are used and accessed as intended under all circumstances. It's kind of a basic definition of what security is. Any software defect may violate the security of a system. Language safety can aid security by assisting in the construction of correct software and finding defects sooner, limiting the effect a defect may exhibit, including limiting access to other parts of the system. And it's that second point that's fairly critical. So a key property of a secure system is something known as the non-interference property. Okay. So the non-interference property basically says that a safe system won't provide access to what's referred to as a low resource, or what's referred to as high resource with low input. Okay, so the basic idea here is you shouldn't be able to access the secret, right, unless you're authorized to access the secret. Now the non-interference, it's a property of correct software, but it's what's known as a hyperproperty. It is a generalization of both safety and liveness properties. And it is not expressible simply as a safety property. The non-interference property holds if and only if any sequence of low inputs here will produce the same low outputs, regardless of what the high-level inputs are. Now that's a little tough to figure out. How does that relate to memory safety? So we're going to connect the dots here. There's this great paper. If you have to read one paper out of all of this, especially if you're at all involved in language design, go read this paper. There, so you can see who the authors are. I'm not even going to attempt to pronounce their names. The meaning of memory safety. So this defines memory safety in terms of a frame rule. Right? A frame rule, a verified program can only affect a well-defined portion of the state with all other memory regions left untouched. It's the basic definition of the frame rule. It's inspired by separation logic and the ideas of local reasoning. I have not been able to find anything yet that says whether or not a frame rule in and of itself qualifies as a safety property or not. So the paper goes on to show that this frame rule satisfies the non-interference property. Okay. So the frame rule relates very closely to John McCall. I think John McCall's here.
He's here.
He's here. Hi, John. John McCall's law of exclusivity from Swift. Or if you've been working in Rust, you have the Rust borrow checker. Or the val language, which is an experimental language. There were some talks on it last year, which tries to get exclusive access through whole-part relationships and value semantics. So all of these things are going after a frame rule. And in doing so, they're going after the non-interference property. Okay. So another way to state the non-interference property is a program can neither affect nor be affected by unreachable parts of the system. Right? And that's what it means when you have exclusive mutable access. Two parts of your system can't interfere with each other. Oh, I will mention too that in this paper, one thing that they call out as being memory unsafe is JavaScript global variables. And then they go through and cite a whole bunch of places where there's been security exploits on JavaScript local variables because JavaScript global variables, not local. JavaScript global variables because JavaScript global variables don't satisfy the non-interference property, and that makes them susceptible to exploits. So memory safety in C++. Well, we have shared mutable references, which make memory safety, as defined in that paper, nearly impossible. Okay. Sanitizers can help, but at a performance cost, which also rules them out in production code. If you're using sanitizers and you're trying to protect your system from security, you also have to be fuzzing the system, okay, to make sure that you have good coverage. And no safety property, in fact, no correctness property at all, can hold in the presence of undefined behavior.
Can I ask what is a fuzzer?
What is a fuzzer? So question was, what is a fuzzer? So a fuzzer is typically a system that will permute your inputs typically looking at traces of your code, so it's a guided permutation of your inputs to try to make sure that all of the code paths are executable. Okay, so and fuzzers, there's a lot of technology built around fuzzers, so you can do things like start a fuzzer against a JPEG reader, and the fuzzer will figure out how to construct valid JPEG files in the process of fuzzing your JPEG reader.
There have been talks given on fuzzing here at CppNow. So if you look on the CppNow YouTube channel, you will find talks given on fuzzing and on fuzzers, how to use them.
Yeah. So no safety properties can hold in the presence of UB, and that's a problem. Okay. So C++, as it stands, cannot provide any safety properties, right, or any correctness guarantees from a language standpoint. Right? That doesn't mean you can't write correct code in C++. It just means that you can also always write bad code in C++. The language will allow it. So all of this is well and good, but I wanted to put this quote in because I think that this is important. Understanding why software fails is important, but the real challenge is understanding why software works. I think far too often people get obsessed with safety properties and with trying to prevent the bad things from happening. And it's a little akin to, if you're selling chainsaws, you can put the guard on the chainsaw so that when it kicks back, it's going to stop the blade instantly and not slice your forehead open. That's a good thing. But you can't make a chainsaw fundamentally safe, right? You can't prevent somebody from using it in a bad way. And so it's very important that you want to always be aware of what the ultimate goal is. The ultimate goal is that we're writing correct software, right? That's the goal. Safety is something to assist us in writing correct software and to limit the blast radius when we make a mistake and we write bad software. Okay? That's what safety is about. And safety, in some sense, is an illusion. Okay? What do I mean by that? I mean, safety is always defined in terms of a given level of abstraction. If you're trying to implement a safe language, one of your safety properties is probably your code can't access uninitialized variables. Okay? Even if you have a frame rule, you'll find that safety property will fall out of your frame rule. But the language implementation itself has to initialize the memory. Okay? So the language implementation itself, in order to provide that level of abstraction and those guarantees, has to violate those level of abstractions and guarantees. And if your system's Turing complete, you can always flip that the other way around. Within a safe language, any safe language, Haskell, I can define a C machine, right? I can create a virtual environment, and I can, within that, execute all the safe code, all the unsafe code with all the same unsafe safety ramifications. Okay? If you go on the web, you can find websites that let you simulate every version of classic Mac OS up through all the versions of Mac OS 9. And you can run an old classic Mac OS on your machine. Now, if you are old enough to have worked with the classic Mac OS, these are machines that had no MMUs. Every process was running in the same address space. There is absolutely no safety guarantees. Any application can stomp on any application. And these things in the simulator are connected to the internet, okay, through a simulator pipe. So all of that unsafe code has all of the same violations. It's just within this universe, okay? So safety is somewhat of an illusion, right? When you're defining the correctness of a system, you're defining it at a particular abstraction layer. And the reason why this is important is because as a developer, since safety frequently comes at a cost, right? It comes at a cost in expressibility, it comes at a runtime overhead cost, it comes with some cost. As a developer, the first thing you do is you think, how could I eliminate this cost, right? Well, I know I'm working in JavaScript, which is a relatively memory-safe language. It's trying to be quite secure. I could implement asm.js, and then I could compile all my C code, and I could run it inside of JavaScript with all the security implications that running the C code in your JavaScript environment implies. Okay, so even within the language, you see people in Java recycling objects to avoid the overhead of the garbage collector. That's circumventing the safety of the system, right? You don't have the same initialization guarantees when I'm recycling an object. Okay. You'll see people say, oh, in JavaScript, or in any reference semantic language, I have all of these objects that are heap allocated. I don't want to be heap allocating all my objects. So what I will do is I will allocate a bunch of parallel arrays of primitive objects like integers, and I will treat slices of those as if they were my objects. Well, I'm removing all of the type safety when I do that. Okay? Now the type safety is on me as the developer, not on the programming language. So safety in some sense is an illusion. Right? It's a tool to help you reason about your code and prove your software is correct. So it can always be circumvented, and often is for performance and expressibility. Ultimately, it's a tool for local reasoning. So can C++ be memory safe? Not without significant changes. Right? It will require an explicit safe subset, right? It requires a shift in the abstraction level, right? If you have C++, to get memory safety in C++, you need C++ with no shared mutable references. That's not C++ anymore. That's not the code that most of you have written in this room, okay? It's that required shift in the abstraction level. Right? So where does C++ go from here? Right? Maybe we can find some direction. So C++, now what? Well, consider a higher level memory safe-ish language where performance isn't critical. Right? TypeScript is usually my recommendation as something that is well supported and fairly ubiquitous. Python is another option. For performance critical components, Rust, maybe Swift. Swift isn't as ubiquitous as Rust at the moment. Complaints about Rust. There's no specification. Bjarne gives this as a call out about Rust. This is actually important. Swift doesn't have a specification either. Correctness is defined with regards to a specification. If you don't have a specification.
There is a specification now. Pharisee wrote one.
Swift has a specification now.
No, not Rust, sorry.
Oh, Rust has a specification now.
Called Pharisee wrote a specification.
Nice. So I stand corrected. Rust now has a specification. Rust is a single source tool chain at the moment. If you're doing commercial software, that's a problem. That's a potential single point of failure in your system. And Rust really has poor C++ interoperability. There are several projects trying to address that. I've been playing with several of them recently. Not great. Are there any professors? Oh, question here.
I believe if you're referring to single source toolchain as there being one compiler, I believe they're working on a second one with GCC as the backend.
I have seen that. So the comment here is that there is some effort to make GCC as a backend, which also helps, but potentially not commercially friendly. So we need a second source commercially friendly compiler too. Professors and grad students. Are there any professors or grad students in the room? A couple. Here's what I'd like to see. I'd like to see an undergrad course on the practical construction of correct software. Okay. So I went looking. I couldn't find a course that met the criteria. I was looking for. The closest is a CS 6115 certified system software course out of Cornell. But that's a graduate level class and too much theory and math for an undergrad level. But what do I want to see covered? I want to see design by contracts covered well. I want to see safety properties covered well, right? And some basics of temporal logic go along with that. I want to see local and equational reasoning covered in the course, along with whole part relationships. It's very important for reasoning about code. I want to see the frame rule, law of exclusivity, come into play here. Okay, and error handling touches on this. So take a picture of the slide, make this happen. So I've given a series of talks, some of them here, some of them at other conferences, on better code. Can I put it back? There you go. Got it? Okay, so I've given a series of talks, some of them here, some of them at other conferences, on better code. And all of my talks have a rubric, right? A goal that we state. And it's almost always stated in the negative. No raw loops. How many people have heard no raw loops? So I wanted to go back and revisit those. The fact that they're a negative statement, I don't think is really quite a coincidence. It's because all of these rubrics, all of these goals are pointing at safety properties. Okay. So let's start with an easy one. No raw synchronization primitives. Right. And we're going to figure specifically on mutexes, because I don't have time to go through all the raw synchronization primitives. Here's a quote from the C++ standard. It's a wall of text. You don't have to read the whole thing, so I'm going to highlight the important parts here. Programs that correctly use mutexes behave as if the operations executed were simply interleaved. Any program that behaves differently has undefined behavior. Okay, that's a note in the C++ standard. It's actually a fairly well-known result around mutexes and synchronization primitives. Okay, what that means is that the correct use of a mutex is equivalent to the use of a serial queue. And yet we don't have serial queues in the language. Okay, so what's the problem here? Well, when we talk about safety properties of mutexes, what safety properties would a mutex assist us with? Anybody? Can you name a safety property that a mutex would assist us with? No races. Okay. No race conditions. Does it? Does it help us with no races? Kind of. Maybe. Right? Because what's the problem here? I can't put it in the phrase of saying, if no operation in my system did blank, then my system as a whole will do blank. I can't make that statement around mutexes and no race conditions.
Concurrent access.
So not quite. What's that?
I would have said concurrent access.
Concurrent access, yeah, almost. So that's what it's going after, but it really doesn't have any safety properties in and of itself. What safety properties do mutexes hinder? Deadlocks. No deadlocks. Okay. So invoking a mutex while satisfying all the preconditions of the mutex, you can still deadlock. In order to show that you don't deadlock, you need to understand a set of extrinsic relationships external to that mutex that break local reasoning. Okay? A mutex is not a safe construct. A safe alternative to a mutex, as I mentioned before, is a serial queue. And generally, serial queues actually tend to be faster in practice because they narrow the scope of the underlying lock. Frequently, they can be implemented lock-free with purely atomic operations. But it's a non-trivial transformation to restructure code from something that was using mutexes into something that's using serial queues, and it also often requires the addition of continuations, because you need to get the results back out of the things from your serial queue. Okay, so let's take another one of my rubrics. No raw pointers. Okay, what I mean by raw here is unencapsulated pointers. So it's shared, unique, T star, no pointers. Cut it out. But we're only going to look specifically at shared pointers, because I don't have time to cover all the other pointers. So what safety property do shared pointers assist us with?
Memory leak,
Memory leak.
accessing stuff that has to be allocated. Destroy.
What's that?
Use after free.
Use after free, right? So lifetime. Object lifetime. Okay. Now memory leaks was also mentioned. Do they give us the guarantee of no memory leaks? No. Not quite.
Assist us with.
They assist us with. Yeah, we'll give it half. Hinders.
Local reason.
Well, yeah. No memory leaks. Anybody know what that is over on the side there? Picture, kind of faint, just appeared. Somewhat beautiful spirograph image. So, how many people here have ever used Xcode? Okay, a few people. So Xcode actually has a nice feature called Memory Graph, which lets you graph memory and look at memory leaks. That is one heck of a retain cycle. Okay, there is a single anchor just about a little past 12 o'clock. You can kind of see everything comes together in one dot. Okay, so that is one object which is held by this network of objects. Every little node in that is another object in that graph. And this was from an actual system. Okay, and if you notice, it's not even quite symmetrical. There are lines that cut across the middle. That's because it's not just an arc of many cycles from this one object that all come back to that same object, but some of those branch in the middle and come back. Okay? That took me like 2 weeks to untangle that mess. Okay. It hinders no race conditions, right? If I have shared mutable access to my data with shared pointers, okay, then if I start handing those things across threads, I've got race conditions. It hinders my ability to guarantee that my class invariants aren't broken. Okay? So if I'm in the middle of some operation, okay, some private operation on my class where I'm going to be breaking my invariants and I have to restore them before I return from my class or from my private method or my public method, right? So, but at some point there, my invariants are broken. Well, I'm working on the guts of my object, and I make a call to some other part of the system. Maybe through a callback, maybe it's just another API call, and that thing accesses a global variable or something else, or spins the event loop, or somehow comes back and references my object. Then that thing observes my object with broken invariants. Okay? And it sounds like it wouldn't happen. It actually happens a lot, right? Right? How many people have ever seen this happen? Okay, yeah, so 30% of the hands in the room. It breaks our non-interference principle. It's a violation of the frame rule. Okay. So if you have shared mutable access to objects, you don't have a frame rule, you don't have non-interference, you don't have security. So what's a safe alternative to shared pointers? Value semantics, whole part relationships. Been talking about this for 15, 20 years. It's easier to reason about, but it requires sometimes difficult code transformations. Okay? It's difficult to rethink a system in terms of whole part relationships from a network of objects. So we'll do one more here. No raw loops. Right? What do I mean by raw? Again, I encapsulated. Raw means unencapsulated. Okay? So, all your raw loops, right? While do for loops. Safety property of loops. What safety properties do loops help you with? What's that? Boundary? A while loop helps you with boundary? Right. Yeah, nothing. Loops don't help. What do they hinder with? They hinder with trying to prove termination. Okay? And here we get to play Jeopardy a little bit, right? We're supposed to always phrase these in the terms of a negative property, but saying that they do not allow not terminating is too many knots.
Isn't termination a liveness property?
Isn't termination a liveness property? It can be, but you can also come along and you can say, well, if all of the operations in my system are guaranteed to terminate, then my system as a whole is guaranteed to terminate. So it can also be cast as a safety property, but that's not typically feasible for an entire system. So, time constraints. So I wanted to bench this as performance, but performance isn't really a safety property. But time constraints is, right? You can say, I've got a real-time constraint. This has to happen at a particular point in time or within a particular envelope in time. Okay, so what I'm trying to get to here is the fact that it's very difficult to analyze the complexity of a raw loop, whereas if you're using an off-the-shelf algorithm, hopefully with documented complexity, you have a better shot at hitting time constraints. I'm stretching a little bit. The important one here is bound safety, right? You're much less likely to have an off by one error if you're passing a range into an algorithm than you are if you're coding the algorithm from scratch. Given that, I think I've told this story, there's a take-home test for people who are interviewing for the Photoshop team, which is a binary search problem. And the number of binary search problems that I've looked at, or solutions that I've looked at that access memory off one end or the other of an array is shocking, right? Probably on the order of 20 to 30% of the answers I've received over the years.
I think that depends on the type of the loop, though, right? Like for index-based for loops have that problem. Range-based for loops are there exactly to eliminate that problem.
Are exactly to eliminate the problem. So the comment here was like index-based for loops exist to help eliminate that problem, and that is absolutely true. And I put them more in the encapsulated loop category, right? If you actually go back, my C++ seasoning talks about sometimes it's okay to use for if you're doing like a simple transform. So the other thing is raw loops can run afoul of the non-interference property, right? And that's an extension of the bound safety issue, right? You can run over the end, and now you have part of your software interfering with another part of your system. So safe alternatives to raw loops, algorithms. They're easier to reason about. They're usually faster. There's no real downside, right? People complain. Classically, my whole story around a rotate and raw loops was because in a code review, I was told that I couldn't use rotate at Google because nobody knew what rotate was, and instead I should code the for loop to do the rotate. And in fact, the code loop, the recommendation was that the loop be coded in a way that was quadratic. So I was like, great. So some people think there's a downside. There's no downside. So I'm going to put in a forward. So this talk I'm actually going to give again at CPP on C in a couple months. And it will be a keynote talk there, so not a keynote talk here. Keynote talks, I think, should inspire the audience a little bit. should give people something to discuss when they leave the room. And so I'm going to start a new thing whenever I give a keynote. I'm going to put a foreword at the end of my keynote, right? Because hopefully this is the start of a lot of discussion. And I'm glad that my talk here is coming at the start of this conference and that it's very well attended. In 2007, I gave a Google Tech Talk titled A Possible Future of Software Development. More than 15 years ago now. And I had two conclusions in that talk, which is what the industry needs is a large library of proven generic components. So data structures and algorithms that are well vetted, that are high performance, that are proven correct. Okay? We need a very large library of those components. I'm not the only one who was saying this. In 2002, when I first met Alex Stepanov, he came to Adobe and gave a whole lecture on this, and that lecture's online. But we need that. But the other thing that I think we need is a small number of non-Turing complete, what I refer to as declarative forms, okay, for assembling the generic components. Okay, and what do I mean by that, right? If you want to build an application out of this generic components, you shouldn't be sitting down and writing code. You should be writing a description for how those components connect together. And you need a few different forms because you need to represent different structures. So you need kind of a small set of domain-specific languages that let you specify how to assemble structures that have particular properties and particular behaviors. Okay. An example is something like a formal grammar, right? A grammar tells you how to assemble a bunch of low-level recognizers to perform some purpose. And within that space, you can do a bunch of analysis about your grammar. Okay? But a grammar won't let you express everything. There has not been a huge amount of progress on either of these fronts in the last 15 years. There's been some. I wish there had been more. But I want to amend this a little bit. And to help you understand why, I'm going to give a walkthrough. Who knows what Daphne is? It's like the only code, 2 people. 3 people. Okay. So Daphne is a verified programming language, and it comes out of Microsoft Research. Daphne 4 was just released. It's actually a fairly active community, mostly on the academic side. Who here has ever heard of TLA+? Okay, so a little bit similar vein to TLA+, but TLA+ isn't really writing code directly, right? TLA+ is a temporal logic system. We talked about safety properties and liveness properties. That's part of temporal logic. Leslie Lambert, who defined those things, also built a system called TLA+, and that's a system for formally proving temporal logic about systems. Specifically, it's targeted at concurrent systems, which is where a bunch of his research is. Daphne has a little bit different flavor in that it's an actual programming language. It compiles down to a bunch of other different programming languages. One of those is even C++. So I could take this code and compile it into C++. Okay. And the idea with Daphne is you can just write your code, but as soon as you start writing assertions, right? Ensures is a post condition up here. I don't have any requires clause, but requires would be a precondition. You can see I have some loop invariants down here. As soon as I start writing assertions, the compiler checks them live. And if you're using VS Code, it actually gives you this error message right in your editor. And it's analyzing your code to prove your assertions are correct while you're writing the code. And the game becomes not can you convince yourself that the code's correct, but can you convince Daphne that the code is correct? Okay, so it's an assisted way to write proofs. And it's kind of nice because you can always, if it's giving an error like this, I can always just comment out that invariant and run the code and see what it does, right? So I can run the code and debug it. I don't get stuck, and then I can try to put my invariant back in and try to figure out how I'm completing my proof. And so I was working on this little piece of code. All this is doing is reversing a sequence. A sequence here is like a C++ view, right? It's a constant thing. I can do takes from it, things like that. But I'm going to take a sequence, which is like a view, and I'm going to create a new view of that sequence, which is the original sequence reversed. So that's what I'm going to do. Okay. So in my loop here, what I'm going to do is I'm going to keep taking the first thing from the front of my list. I start with my sequence A. I'm going to take the first thing off, and I'm going to append my remainder, which starts emptying on the end. And so one element at a time, I'm going to reverse all of the elements in my sequence. Okay, so people kind of see what's going on, right? The remainder is 1 dot dot dot. And I have to stop my loop a little early and do a remainder plus R on the outset because Daphne doesn't understand how half-open intervals should work, so 1 dot 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 will give me an index error if I don't at least have that first element in there. Darn it. Now I got to go fix Daphne too. But I'm writing this, and I got stuck. I got stuck right here. This invariant is true. Okay. What is this invariant saying? The little absolute symbols there are lengths. Okay. So what am I saying? I'm saying that for all I within the sequence, R sub I, R is my result here, is equal to A sub R minus I minus 1, which is basically saying that I've reversed my sequence up to some point. That's a loop invariant. At each step, my loop invariance. That's a true statement. But Daphne can't prove it. And I don't know what to tell Daphne to prove that statement. And I'm stuck. This is frustrating. This is why formal methods are so friggin' hard. Okay? So, and it's correct, but I can't get the system to see that. So I try Googling, I read a bunch of Stack Overflow stuff. I'm still stuck. I can't find the answer. What the heck am I supposed to tell Daphne to complete this proof? Anybody here who's used Daphne? Dave Single doesn't count. Who would know what I would have to put in here? Anybody here who hasn't used Daphne, who has a conjecture on what I'd have to put in here?
Zero lengths, like empty input?
No, I'm good on the empty input. I'm good on empty input. So my for all doesn't apply if it's empty there. It does get that part of my half-open interval correct. So there's no mistake there. I'm just missing completing the proof. So, what's that?
I was going to ask if you asked ChatGPT.
Yeah. So I went to Bing Chat and I said, how can I strengthen the loop invariant in the following Daphne code to convince Daphne that the loop invariant holds? And then I pasted that code in. Okay? This shocked me. This was out of total desperation. This is the answer I get. You could add an invariant that ensures that the elements of remainder are the same as the elements of A that have not yet been added to R. Here's an example. Invariant for all, I in the range of 0 to length of remainder, implies remainder of I is equal to A sub length of R plus I. This invariant states, it's going to explain this to me. This invariant states that for all indices I in the range, 0 to remainder, the ith element of remainder is equal to the I plus length of R element of A. This ensures that the elements of remainder are exactly the elements of A that have not yet been added to R. That's the answer I got. That's 100% correct. I put in my invariant, and now I was able to uncomment my post condition, and now that's a proven, formally validated piece of code. Okay? I have a suspicion. I have found that AI systems, both Copilot, ChatGPT, Bing Chat, do better with Daphne code than they do with other languages, especially than C++ code. And my hypothesis is they've been learning on all the body of code out there in the environment, and most of that code in C++ code is wrong. And all the Daphne code is correct. Okay? So the system actually does a good job. So I want to amend this. A large library of proven generic components, a small number of non-Turing complete declarative forms for assembling the generic components built with AI-assisted verification. So 2 fundamental things have changed in the last 15 years. So there have been great strides in how we prove systems correct, and the computational horsepower of the machines that we are executing on makes it feasible to prove the correctness of software. The fact that Daphne can check my code, validating it for correctness while I'm typing it in the editor, in and of itself is stunning, right? Even if it can't always connect all the dots, right? I didn't change my code there. My code was correct. I just had to help Daphne figure out that my code was correct. And then large language models sitting on top of that can help us assist those systems to complete those proofs, right? So we're at a stage where I think it's actually feasible that we can start defining languages and defining systems where we can write provably correct software, right? And provably correct software has all the safeties. So closing. Memory safety is important, okay? So I've seen too much stuff about it being propaganda and hype. It absolutely is, but it is important, okay? Correct software is important. Shipping software without defects is important. Use of safety properties so your code doesn't do bad things is something that you can do today. When you're writing a piece of software, think about this operation, this piece of code that I'm constructing. If this is used correctly, what safety properties does it assist with, and what safety properties does it hinder? Okay? Can you build components that let you construct your system in a safer fashion, right? Even if you don't have a safe language protecting you on the back end. And don't lose sight that safety isn't the goal, correctness is the goal. Okay? Because the safest car is the car that doesn't go anywhere. Right? So that's the end of my talk. I'm happy to take more questions.
Just a small comment about the last example. It's only true if none of the cars go anywhere. So even if both cars go anywhere, someone could come into it.
Yeah, so the comment is, your car isn't safe even if it doesn't move, if other cars are moving around you. Yeah, true.
I think the next big thing in the industry is going to be self-stopping cars.
Timur.
So I have to say, I'm not a computer scientist. Like a lot of the background here, I'm kind of missing or filling in the blanks. But one thing that you mentioned, I think earlier in the talk, you said there's these safety properties and liveness properties.
Yes.
And you said that if you can prove both, you can prove total correctness.
Yes.
Isn't that something that is just not provable in principle? Because A, the halting problem, and B, whenever you do this kind of stuff that you showed with Daphne, as soon as your code gets more complicated, you will just always hit like a point where like it's just not provable because we have like Gödel's incompleteness theorem and the
Right.
halting problem and all of these things.
So
it
there's
just doesn't seem to me that this would scale basically to
So-
more complex code that actually does something real.
yeah. So comment on the halting problem first, because there's a lot to unpack in Timur's statement. So I'll try to repeat pieces of it as I go here, and you can let me know if I miss any pieces. So he said, proving total correctness is proving safety properties and proving liveness properties, but you can't do that because of the halting problem. Well, I can write a program that says, int main, curly brace, and I can prove that that terminates, right? The halting problem is taking an arbitrary system, right? Some unstructured morass of code, and fundamentally it may be undecidable whether or not that code will terminate or not. So that's a very different thing than what we're talking about here. The problem where we run into the halting problem is if you say, oh, let's prove that Photoshop 30 million lines of C++ code will terminate. You're probably in halting problem territory at that point, right? You're trying to take an existing system. What the halting problem doesn't talk about is what can you prove about software that you're constructing, right, a piece at a time to prove the system as a whole. This is where Bertrand Meyer's work on design by contract, why that's so influential, is because it shifts our abstraction level to say, oh, if we can prove that the post conditions of each of our operations will satisfy the preconditions of the subsequent operations, then we know that our system as a whole will make forward progress. Now, in order to prove that on an individual function, we need to prove both the safety properties and the liveness properties of those things. It's also total correctness means something very specific there. So you have the partial correctness of a system says that if a system does terminate, then it satisfies the post condition. That's the definition of partial correctness. And total correctness is partial correctness plus it will terminate. Okay? And the safety and liveness properties let you decompose that into an operation at a time and show that then you can reassemble the whole thing, right? So does this stuff scale? It does, because at each level, you're moving up to another abstraction level as you assemble your system, right? You don't keep building a system, we do unfortunately, but you shouldn't keep building a system out of millions and millions of small primitives all interconnected. You build some abstraction points. Those abstraction points have a set of guarantees that are bounded, and so kind of at each level you can keep adding a level of the stack, proving each level as you go up, and then you prove the system as a whole. So it is tractable. Dave Sankel kind of pointed out that the probability that you make a mistake at any level, right? And you can make a mistake in the specification as easily as you can make a mistake in the code. In fact, it's probably more difficult to get the specification correct, right? Try writing a correct specification for what does it mean for sort to sort. It's a little non-trivial, okay? If you make a mistake at any level in that stack, those mistakes compound, okay? And you get a higher and higher and higher and higher probability as you go up that your system as a whole is going to fail. So, and it's a multiplicative effect, so it accelerates rapidly, okay? Which is why it's very difficult to build a complete provable system. But the fact that we can't build a complete provable system is where safety comes into play. Okay, we can at least provide a set of guarantees, and safety properties themselves compose. So we can at least provide a set of guarantees so that when something goes wrong, the blast radius is limited. We can do that. So we can also strive for that correctness goal, right? If you don't shoot for totally correct, if you accept the fact that all of your code is buggy, that's just increasing your coefficient on all of those multiplications, right? You guarantee you're shipping expletive, okay? Okay, so we had this conversation with Dave Abrahams, and Dave Abrahams was like, I completely understand we can't build correct system, and yet we must behave as if we can, okay? Because there isn't an alternative. So did I miss anything in your comments there, Timur?
I guess I have a very quick follow-up question then. You're saying that this stuff applies to kind of you say it's feasible as a scalable approach if you write new code from scratch and you build it, following those principles. But I think guaranteeing safety for writing new code is actually not the hard problem. The hard problem is, it is a hard problem.
Mhm.
The much harder problem is, what do we do if we have to call into existing legacy code, which we all have to do?
Yep.
And what do we do then? And I think that's the problem that a lot of people have no idea how to solve or even how to tackle.
Right. So to echo here, he said, a lot of times we're not writing fresh code from scratch, right? We have to call into other code. That code may or may not be correct, may or may not be documented. We have to kind of do our best to say, what are the preconditions of the thing that I'm calling, okay? And make sure that I'm staying within those preconditions. And sometimes that means you have to be conservative, okay? It means you have to say, well, I'm just going to stay away from the boundary cases, right? It used to be a common technique on old Mac operating systems. They had no VM system, and so they'd run out of memory. So if you were going to make a call and that call would fail catastrophically if it ran out of memory, what you would do first is you would allocate a big chunk of memory to make sure that you could get it, and then delete it, and then make the call. So we call that pre-flighting.
Yes.
Okay? So you would have to pre-flight the call before you do it. Sometimes you have to resort to those kinds of tricks, right when you're dealing with code. One thing that I find very annoying is oftentimes, like even when people are working in C++ and they're calling an algorithm, and the algorithm is very well specified. It says exactly what it does, exactly what's required of it. Modulo my complaints about C++ specifications. They don't even look at the docs, okay? So I can give you numerous examples of people just calling C++ functions, and they hand them comparison functions that have state. They hand them things that don't conform to the requirements of that function. They try to sort arrays of things with nans in them. It goes on and on and on and on. And then they're surprised when it fails, okay? And this goes back to the education process, right? People haven't learned that there's no piece of code. It's almost impossible to write a piece of code that has no preconditions, okay? I posted on Twitter recently, if you took two arbitrary integers and you multiply them together, what's the probability you get undefined behavior? Two ints, multiply them together. Probability of undefined behavior. It's like 99.69% of the time you get undefined behavior, okay? Because you overflow, right? Most pairs of integers, the vast majority of integers that you multiply together will overflow. It's almost impossible to find two integers that won't overflow. Okay? So, what's that?
I have an algorithm for finding two such integers.
There we go. Right? So, most engineers don't even think in those terms, right? They don't think, I'm constructing this set of things at each level, at each statement that I have to write. I have to understand what are the preconditions that allow this operation to work. Am I upholding the preconditions for that operation? What impact does me upholding the preconditions of that have on my interface? What are the preconditions of my function so that I'm upholding the preconditions of everything I'm calling, right? That's how you want to be constructing right software, but people aren't trained to do that, right? And I think that that's unfortunate.
So if you maybe go back to the slide with the different three bullet points of like a library of generic things and the AI system, whatever.
Yeah.
So I think that as C++ people, a lot of our world is like within that first bullet.
Yes.
It's just trying to find and implement and increase that size of this large library, and making and trying to make our products provably correct.
Yes.
So
if I am inside that first bullet, is it like turtles all the way down? Do I also implement my own generic component in terms of lower level generic components that are proven
Ideally, yes. I mean, that's, hopefully these things compose, right? And I think something that's being slowly addressed in the standard is the original algorithms that went into the STL were not the original algorithms that Alex wrote for the STL. It was that cut out half of them because they didn't think they could get everything into the standard, and people thought some of them were just too theoretical. And now we're kind of going in and we're backfilling, right? We have transform, which everybody else calls map, but basically if you have a map and reduction as primitives, you can build most of the rest of STL out of those components. And so yes, very much what you want is foundational layers. And at the bottom you have ones that are nearly semantically void, right? A base reduction doesn't do anything. It has almost no meaning. It's got a set of axioms around it, right? But it doesn't have meaning until you plug in actual types and actual operations into what that reduction is. Maybe it's a sum, maybe it's a product. And so at the bottom, though, you want these fundamental abstract layers. And as you build up, you want the things that have more semantics and more meaning, right? Just because you have reduction doesn't mean you don't want sum and product. You still want sum and product, right? Right? So you want that whole stack.
When it comes to semantics, like, is there an AI assisted way to make sure that a lambda is associative or commutative?
Yeah, I mean, the interesting thing is, Daphne can handle a bunch of that, right? It's got universal and existential qualifiers. So you can say, for all A and B, A must be compare less than B type of thing. So yes, so I mean, that's kind of the whole point, is that you can prove those higher level properties. It also deals now fairly well with finite arithmetic. And so it will tell you, if you tell it that I'm using a fixed sized integer, it will tell you, but this could overflow. Okay. Question here.
So the definitions of safety you were providing, they usually refer to programs, not to code bases, correct? I think that's a distinction, right?
Yeah.
Because there's a definition of safety that nobody talks about, which is definition safety. The idea, and we talk about in the standard, it's called the one definition rule, is how we phrase it, right?
Right.
Like these axioms, these theorems, they all suppose you're being coherent in the first place, which is maybe not something we can grant. So I don't know if you have any comments about like correctness and safety in the face of, I'm not even sure your code is built in a coherent manner.
Yeah, and like I said, when you're coming at it from a large system, who was it? Was it Dave Senkel who talks about bubbles of, you kind of want to create little bubbles of correctness within it, right? And one of the beautiful things about generic programming is you can introduce generic programming into an existing code base, regardless of whether or not that code base was written in a generic fashion. Maybe it's object-oriented, maybe whatever. Generic programming is defined in the absence of any larger framework. So making a system object-oriented is very difficult, and introducing object-oriented into paradigms into something that's procedural is very difficult. But introducing generic components into something that's procedural or object-oriented or whatever it is, or functional, works. And in the same way, introducing correctness and introducing preconditions and postconditions and class invariants into an existing system works and will help you. Okay, there's no magic bullet, and in fact, I work on a product that, I spend most of my time when I'm working on a product working on Photoshop. Photoshop has 30 million lines of code. There is no way, and it's 30 million lines of code almost without comments and almost without specification, right? I tell a story, the original author of Photoshop was very much against comments. He said they were always out of date and misleading, And so no comments in code was the rule when I started on that project. So it's not a joke. It's like this morass of 30 million lines of code with almost no comments. And now it's a problem as we try to hire more engineers to work on the code base. But that doesn't mean that you can't take these principles and start to inject them into that a piece at a time.
So it's necessary, but I guess I'm saying, like, in some ways we talked about another cars can hit your stationary car. This is kind of one of those points where it's like, it's not sufficient though. Like,
yeah,
like,
it's not
if
going to
your
get you all the way
language
there.
model is That's great, but if your language model supposes spherical cows in the sense of you have single source build systems to be something else. But if you have like one monorepo with one version of everything, and there's no way to be confused about what version of what dependency is being used in what translation unit. Like, if you suppose all that, then your language models like actually shows you can't crash in these circumstances or whatever.
Right.
But absent that, which very few people have, in fact, it's pretty rare that people do have that, probably even in those safety sensitive systems.
Yes.
Like, we're talking about pretty massive gaps in the safety of like the worldwide code base, right?
Yes, there are massive, massive gaps in the worldwide code base regarding both safety and correctness.
So going back to your no raw loops, which is a very unpopular concept in scientific computing in particular. So obviously, right, like the moment you get into C, you can overflow, you can make mistakes, right?
Right.
That's the part of the point here. How do you bridge the gap between that and most of my literature that I'm working off of, or most of the algorithms I'm reading, are written in index-wise notation, are index-wise sums because they came from mathematicians. They are, index-wise operations because that's the natural way to express things in mathematics.
As opposed to iterator-based.
Exactly.
Right.
Exactly.
So this is why I want a large library. And you can help build that, right? You want these algorithms expressed indexed, write the algorithm as an algorithm expressed as indexed. Maybe feed it into Daphne, make sure you get it correct. Have that in C++ code and put it in a library, right? That's kind of the vision, right? I always say, like, for any algorithm, what do I want for the algorithm? Well, I want kind of all the forms. I want the index form. I want the iterator form. I want the in situ, the in-place form of the algorithm. I want the greedy functional form, which is the copying form of the algorithm. I want the lazy form of the algorithm. I want the parallel in situ form of the algorithm. I want the parallel greedy functional form of the algorithm. I don't think there really is a parallel lazy form of the algorithm. But I want, I don't want one find. I want 150 finds, right? All nicely organized and categorized so that I can say, I want that find for this problem. Okay? Yep.
Yeah, you have the find finder.
Yeah, I have the find finder. There we go. So yeah, I mean, it's like, that's how you should develop code. And it can even help on your own project, even if you don't share this stuff. It's like, oh, instead of writing my own loop here, I'm going to give it a name, put it in a function, spend a little time with it, and then other people will be able to use it.
So yeah, to follow up on that, when people in scientific computing hear no raw loops, they hear, oh, I should be using std iota.
Right, which they haven't seen my talk.
Right. But with recording,
Yes.
you're not saying that.
I am not saying that in my talk. I am explicitly not saying that in my talk. What I'm saying is encapsulate all of your loops. Okay? Question here.
Do you
5
have
more minutes.
examples of DSLs that kind of do what you would like for this second point here?
So the easiest one is EBNF. There are many layout systems that fall into this category. I've written my own, which is available online. There's Eve and Eve 2, which are layout systems that I've done. There are formatters, which is kind of the inverse of parsers, where if you can find there are some formatters that let you give kind of declarative forms of the formatters that fall into this category. There's schemas, which schemas are kind of a half of what I would consider a declarative form because they define the structure, but they don't define the operations on the structure. The operations on that structure are something that I call sequence models, which would let you describe kind of sequences plus the operation, or schemas plus the operations on the schemas. There's work that I've done the last 20 years on something called property models, which have declarative forms. They're, depending on how you look at them, they're a generalization of functional reactive programming, or they're a constrained form of propagators. So they kind of sit in this sweet spot in the middle. But that lets you specify relationships between discrete properties that have particular guarantees within the system. And if I look at, something like Photoshop, it's like, what do I want to do? I want to be able to declare the model for what's the structure of a document. I want to be able to declare, given the stream of bytes, how do you parse that into that structure? I want to declare the structure itself contains all the possible operations that I can do to manipulate the structure. And so then I want to be able to say, now I want a layout, and I want to connect that layout to all of those structures and put the whole systems together. So those are examples.
Yeah. Would you consider the activity of hooking up different senders in the sender-receiver model into one execution graph as something that falls into the second bullet? And how would you like the standard to make sure to limit or make this the possible graphs non-Turing complete in some way?
Yeah, it is. So the question is, does the sender-receiver model touch on this? It does, in the sense that it's a structured form. It doesn't in the sense that it's not declarative. It's imperative. You're building the structure as you go, as opposed to having a way to declare basically the schema for the structure and all the possible forms that the structure could take. So it checks a bunch of these. I think there's still some holes in it. I keep talking with Eric Niebler. I think cancellation in the system is completely broken and wrong, and that needs to be fixed. And so it's good work. It's better than anything else out there. I still have criticisms of it, but they're not like don't use it. It's a step. So.
For your second bullet, there's a paper from the 60s called The Next 700 Programming Languages that describes exactly this.
Yes.
And describes it in a way that those languages are all interoperable, but help you do those small things.
Yes, yes. Yes, and that's what I mean by, these declarative forms. I don't mean them to be like completely disparate systems. They're systems that all connect together. Right? They let you describe a system in its entirety and all of the behaviors and interactions in kind of a guaranteed form. So I am out of time, I believe. Yep, I'm probably over time at this point. I will be around whole conference, so if anybody has questions. Yep.